There is an experiment you can do right now in any physics lab on Earth. You fire a particle at a detector. You don't watch where it goes. It spreads out like a wave, exists in multiple places at once, and hits the detector in a smeared probability cloud. Now you fire the same particle, same setup, same everything. This time, you watch. The wave disappears. The particle picks one definite spot and hits it like a bullet. Same particle, same equipment, different result, because you looked. And here is the thing that should stop you cold. After a century of quantum mechanics, we still have no consensus on the most fundamental process in all of physics. What actually happens when a quantum system is measured. At the Foodie World Science Festival, Brian Greene asked 3 quantum mechanics specialists this exact question, and got 3 entirely distinct answers. 3 experts. 1 question, 3 different realities. This is Photon Path, and today we're going to the edge of what physics actually knows, and what it still genuinely cannot explain. Before we go further, we need to destroy a myth that the internet keeps spreading when physicists say observing a particle changes its behavior. They do not mean a human being needs to look at it. The need for the observer to be conscious is not supported by scientific research, and has been pointed out as a misconception rooted in a poor understanding of quantum mechanics. So what does observation actually mean in quantum physics? To observe a particle means to gain information about one of its physical properties, such as its position, momentum, energy, or spin, by having it interact with a measuring device. That is it, a camera, a detector, an atom bumping into another atom. Any physical interaction that extracts information from the quantum system counts as an observation. You don't need a brain. You don't need consciousness. In quantum mechanics, observation simply means any interaction with a macroscopic apparatus that extracts classical information from a quantum system. The observer doesn't need to be conscious. It can be a camera, a detector, a photographic plate, so why does it matter? Why does a mindless detector change what a particle does? That is the question, and the answer, or rather the lack of a clean answer, is one of the deepest unsolved problems in all of science. Let's build up to it properly. In quantum mechanics, before you measure a particle, it is described by something called a wave function. The wave function doesn't tell you where the particle is. It tells you the Toyn probability of finding it in different places if you were to look. The particle isn't secretly in one place with you just not knowing. It genuinely exists as a smeared cloud of possibilities, simultaneously. This is called quantum superposition, and it isn't a metaphor. It is mathematically precise and experimentally verified, left alone. The wave function evolves smoothly and deterministically according to an equation. The Schrödinger equation, no randomness, no jumps. Pure mathematical clockwork. But then you measure it. Upon measurement, a stochastic process governed by the Born rule collapses the wave function to a single outcome. This dual evolution of quantum states, the core of the measurement problem, has puzzled physicists and philosophers for nearly a century. Here is the problem in one sentence. A theory that perfectly predicts everything a particle does before measurement gives absolutely no explanation for what happens during measurement. Standard quantum mechanics, as taught in physics colleges, postulates that collapse must occur whenever a measurement is done. However, it does not explain which outcome basis should be used, why a collapse happens, or even what constitutes a measurement. Read that again. The textbook says collapse happens during measurement, but cannot define what a measurement is or why collapse happens at all. The remarkable predictive power of quantum mechanics has led most physicists to adopt a pragmatic, shut up and calculate approach. Shut up and calculate. That is a real quote. That is how the most successful scientific theory in history handles its deepest conceptual problem, by telling its practitioners to stop asking questions and just use the equations. But some physicists refuse to shut up, and what they found when they kept asking is genuinely alarming. Here is the most concrete, experimentally verified proof that observation isn't passive, that watching something genuinely changes what it does. It is called the quantum Zeno effect, and it might be the strangest confirmed fact in physics. The quantum Zeno effect is the suppression of quantum state evolution by frequent measurement, named for Zeno of Ilia's paradox of the arrow. At any single instant, the arrow appears motionless. So how can it move? Here is what it means in practice. Take an unstable radioactive particle. Left alone, it will decay in some predictable average time. That is just radioactive decay, completely normal physics. Now measure it frequently, repeatedly. Check it over and over, at very short intervals. If you check whether a quantum particle has decayed often enough, the probability of seeing decay drops toward zero. Watch a particle often enough, and you can stop it from decaying. Literally freeze it in place by looking at it. If you repeatedly measure the atom at very short, rapid intervals, you are constantly forcing it back into its original, undecayed state. This frequent observation prevents the wave function from evolving and effectively freezes the decay process. This isn't a thought experiment. The quantum Zeno effect was first formulated mathematically by Misra and Sudarshan and demonstrated experimentally by Itano and Wineland in Sudi with trapped ions. They drove a transition between two ion energy levels and confirmed more measurements, less change. Continuous measurement, zero change. In the quantum version, looking at the arrow freezes it in place. But that isn't the only thing that happens. The funniest thing is that if I look somewhere, then the arrow cannot go where I'm looking. Physicist Barantini explains, it will have to go around it. It will have to modify its trajectory to go outside my field of view. The particle doesn't just freeze when you look. It actively avoids where you're looking. And the reverse is also true. There is an anti-Zeno effect, where measuring at just the right frequency, Sudi accelerates Z decay instead of stopping it. Observation doesn't just passively record what a particle does. It too actively reshapes what the particle is allowed to do. So why does measurement do this? Why does extracting information from a quantum system change what it does? The entry Interpretations of Quantum Mechanics in Wikipedia contains 13 distinct classes of theories and interpretations, and it does not even account for some recent proposals. 13 for one question. Let's look at the three main camps because they lead to three completely different visions of reality. The oldest and most widely taught interpretation. The Copenhagen interpretation says nothing about the cause of the collapse. It simply says, before measurement, you have a wave function. After measurement, you have a result. What happens in between is not a question physics can or should answer. The Copenhagen interpretation, summed up by physicist D. Merman as shut up and calculate, renounces addressing the question. The universe isn't hiding a deeper answer. The question itself is malformed. Don't ask what the particle was doing before you looked. Before you looked is a meaningless concept. Most working physicists live here. It is uncomfortable, but it works. The many worlds interpretation asserts the objective reality of a universal wave function and denies the actuality of wave function collapse. All possible alternative histories and futures are real, each representing an actual world or universe. Under this view, when you measure a particle and it collapses to one outcome, it doesn't really collapse. The universe splits. In one branch, you measured spin. Up in another branch, an identical copy of you measured spin down. Both are equally real. MWI removes the observer-dependent role in the quantum measurement process by replacing wave function collapse with the established mechanism of quantum decoherence. There is no collapse, there is no randomness. The Schrödinger equation runs forever, perfectly deterministically, and reality just keeps branching. The supporters are serious physicists like Sean Carroll, Tegmark, and they promote different variants of many worlds as serious contenders for solving the measurement problem. The critics are equally serious. For one philosopher of physics, many worlds would be acceptable only if truly everything else has failed. The third approach says there is randomness in the dynamics, and the deterministic Schrödinger evolution is only an approximation to random dynamics. This is the essence of collapse models. In other words, the wave function really does collapse, not because of measurement, but because of some physical process we haven't fully identified yet. Perhaps gravity plays a role. Perhaps there is a threshold of mass or complexity beyond which superpositions become unstable. Roger Penrose has argued that gravity causes collapse, that quantum superpositions of different mass distributions are fundamentally unstable and collapse spontaneously, without any observer required. This is the most falsifiable option. It makes predictions about 41 collapse should happen that future experiments could potentially test. None of these three camps has won. The cacophony of proposed solutions for the measurement problem is disturbing. It hurts our conception of science as delivering a consistent description of reality. Why, after a century of quantum mechanics, do we still have no consensus on its most fundamental process? This isn't just philosophical hand-wringing. The measurement problem is becoming an engineering problem. In quantum computing, where information is stored in superpositions, qubits, measurement is violence. The moment you measure a quantum system, you force it to make a choice. The superposition collapses, the quantum information is destroyed, and you can never get it back. This isn't a technological limitation we'll eventually overcome. It is woven into the mathematical fabric of quantum mechanics itself. Every time a quantum computer interacts with its environment, every stray photon, every vibration, every thermal fluctuation, it is being measured by the universe. The wave function collapses. The calculation is destroyed. This is called decoherence, and it is the central engineering obstacle standing between us and useful large-scale quantum computers. The quantum Zeno effect has practical applications in quantum state preparation, decoherence-free subspace engineering, and dynamical decoupling for quantum error correction. Scientists are now deliberately using the Zeno effect, firing rapid measurements at qubits to freeze them in useful states and prevent decoherence. We're weaponizing the measurement problem against itself. The question, why does observation change a particle, isn't abstract. Its answer, or lack of one, is actively slowing down the quantum computing revolution. We've built the most powerful predictive theory in science. We've used it to build lasers, MRI machines, semiconductors, and quantum processors. And we still don't know, at the most fundamental level, what we're actually doing when we make a measurement. Here is where we actually are in how quantum mechanics works. It predicts experimental results with more precision than any other theory in the history of science. No experiment has ever contradicted it. And yet, the measurement problem has been haunting physicists and philosophers for almost as long as the century since quantum mechanics was proposed, and remains genuinely, stubbornly unsolved. The three leading interpretations give you three completely different pictures of reality. In one, reality doesn't exist before you look. In another, every time you look, the universe splits. In a third, something we haven't discovered yet physically triggers collapse. All three are mathematically consistent with every experiment ever performed. All three lead to radically different philosophies of what exists, and the fact that we can't tell them apart, that our most precise theory cannot tell us what reality tin. You see, only what we will time measure might be the most honest thing physics has ever admitted. Observation changes the particle. A century of the smartest people who have ever lived cannot fully explain why. That is not a failure of science. That is science being more honest than any other human discipline has ever dared to be. If that idea unsettles you in the best possible way, hit like and subscribe. Next week on Photon Path, dark matter 27% of the universe is made of something invisible, undetectable, and completely unexplained. And it might be what built every structure you've ever seen in the night sky. I'll see you then. Follow the light.